In this video, let's understand quantization in deep learning in a simple and practical way. We'll see why AI models struggle on edge devices, how quantization helps by reducing precision, what the two main types are, and what challenges engineers face while using it. Today, many industries want AI features inside real products and services. But deploying deep learning models directly on edge devices like phones, cameras, or embedded systems is not easy. These applications often need real-time responses, and heavy models can introduce lag, slower predictions, and an overall poor user experience. A big reason for this problem is that most deep learning models are trained using 32-bit floating point numbers. That gives good precision, but it also increases memory use and computation cost. On limited hardware, this can reduce performance and make inference slower than what practical applications need. Quantization is the technique of storing tensors and performing computations using lower bit widths than standard floating point precision. In simple words, instead of using large numerical representations, we use smaller ones, such as 8-bit integers. This reduces model size and allows faster, more efficient operations on many hardware platforms. When we reduce precision, the model becomes lighter. That means less memory is needed, fewer computational resources are required during inference, and hardware can often run vectorized operations more efficiently. So in many real-world cases, quantization helps improve latency without a major hit to accuracy. Now that we've covered core idea check, let's test what we've learned so far.
Here's quiz number 1. See if you can get it right.
Question 1. Why do deep learning models often struggle on edge devices? The correct answer is, they use high-precision computation and can be heavy. Most models use 32-bit floating point arithmetic, which increases memory and computation cost, making deployment on edge hardware challenging. Question 2. What does quantization mainly do? The correct answer is, uses lower bit widths for storage and computation. Quantization reduces numerical precision, such as moving from 32-bit float to 8-bit integer, to make models more efficient. Question 3. Which number format is mentioned as commonly useful in quantized models? The correct answer is 8-bit integer. The article specifically mentions reduced precision or 8-bit integer numbers as a better fit for many edge deployments. The first major type is post-training quantization. As the name suggests, it is applied after the model has already been trained. This is a conversion technique that can shrink the model and improve CPU or hardware accelerator latency, usually with only a small reduction in accuracy. It is popular because it is simple and practical. The second type is quantization-aware training. Here, the model is trained while taking quantization effects into account. In other words, training simulates the lower precision environment so the model can adapt. This often helps when post-training quantization causes too much accuracy loss. Quantization is useful, but it is not free. Since weights are rounded into lower precision values, accuracy can drop. In many cases, a drop of around 1% may still be acceptable in industry. But some models, especially ones with wide dynamic ranges or architectures like BERT, may lose more accuracy and need extra care. Now that we've covered types and trade-offs, let's test what we've learned so far.
Here's quiz number 2. See if you can get it right.
Question 1. When is post-training quantization applied? The correct answer is, after the model is trained. Post-training quantization is a conversion step performed once training is complete. Question 2. What is the key idea behind quantization-aware training? The correct answer is, it models quantization effects during training. Quantization-aware training helps the model adapt to low-precision behavior during the training process itself. Question 3. Which model is mentioned as one that may see more than 1% accuracy drop? The correct answer is BERT. The article specifically notes that some models like BERT may experience an accuracy drop greater than 1%. One major challenge appears during training. Once weights are quantized into discrete values, gradients cannot flow through them in the usual smooth way. That makes backpropagation difficult. To deal with this, approximation methods are often used to estimate gradients of the loss function. Another challenge is convergence. Quantized weights can make the model harder to train properly, and optimization becomes more sensitive. To get better performance, a lower learning rate is often recommended. So while quantization helps deployment, it can make training more delicate. Now that we've covered challenges recap, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. Why does backpropagation become difficult with quantized weights? The correct answer is discrete values do not allow normal gradient flow. Quantized weights are discrete, so gradients cannot pass through them in the standard continuous way. Question 2. What is commonly suggested when gradients are hard to compute through quantized weights? The correct answer is approximation methods for gradients. Approximation methods can estimate the gradients of the loss function when direct backpropagation is infeasible. Question 3. What training adjustment may help quantized models converge better? The correct answer is lower learning rate. The article notes that to get better performance, the learning rate should be low. That's the big picture of quantization. If you understood why lower precision matters and how it affects both inference and training, you've got a strong foundation. In the next step, you can explore the maths behind quantization in more depth.